Hello everyone. Today we'll be defining characteristic function and we'll discuss a few properties. So you have already studied what is moment generating function, what is probability generating function. So characteristic function is kind of similar thing. So let me first state the definition. The characteristic function of a random variable x is defined as phi xt. So you have another argument t coming in picture. Expectation of e raised to itx, where t is any real number, I is of course your square root of -1. Okay, and expectation of e raised to itx you all know can be written as cos tx plus I sin tx. So this is equal to expectation of cos tx plus I times expectation of sin tx. Of course we know that cos tx, mod of cos tx is always less than equal to 1. As a result, expectation of mod cos tx will always be less than equal to 1. Similarly, mod sin tx is always less than equal to 1. Hence, expectation of mod sin tx is also less than equal to 1. So, cos tx as well as sin tx are both integrable random variables, that is their expectations are finite, and hence phi x always exists. Okay, so these numbers are always finite. So, phi x is always kind of finite. Hence, characteristic function is preferred over MGF or PGF, because MGF and PGF exist only over certain ranges of t and s respectively. Okay, so let us consider a few properties of characteristic function. What happens if I consider, say, linear combination of the random variable? So if I define y is equal to, say, ax plus b, where a is not equal to 0 and b is any real number, then how would I define characteristic function of y? So it would become expectation of e raised to ity by the definition. Let me substitute the form for y. So it is expectation of it ax plus itb, correct? Instead of y, I am substituting ax plus b. So it becomes expectation of e raised to it ax plus itb. So itb, these are all constants. As a result, they can be taken outside the expectation. So this can be written as expectation of e raised to it ax into e raised to itb. So e raised to itb can come outside. So this becomes e raised to itb. And now expectation of e raised to it ax is nothing but characteristic function of x at ta instead of just t. Okay. Expectation of e raised to it ax is characteristic function of x at ta. So it is phi x at ta or at I can write instead of just at t. Okay. So phi by t becomes this, e raised to itb phi x at. So knowing characteristic function of x, we can directly compute characteristic function of y. Okay. Now, what happens if I take x, say a is equal to -1 and b is equal to 0. So, y becomes minus x. Okay. So, phi of -xt would actually be, because b is 0, this first term won't contribute. It would become phi x at -t. Okay. And what is phi x at -t? Let me try to write down. Phi x at -t would become expectation of cos -tx plus I sine minus tx. Now cos of minus x is same as cos x. So it is expectation of cos tx minus, because now sine of minus x is minus sine x. So it becomes minus I sine tx. Okay. So this is actually, okay, let me write down expectation of cos tx minus I expectation of sine tx. So this is complex conjugate of the original characteristic function. So it is phi xt bar. Okay, it is complex conjugate of original function. Is it okay? If distribution of x is symmetric around 0, then we know that x and minus x have exactly same distribution. So in that case, phi of xt would be exactly same as phi of minus xt. So it would mean that phi xt is same as phi bar xt, because just now we proved that phi minus xt is nothing but phi bar xt. So a number would be equal to its complex conjugate. This means that imaginary part vanishes. Okay, so there is no imaginary part. It means that the characteristic function is real. Okay, so phi xt is real if and only if distribution of x is symmetric around 0. Okay, that is x and minus x have exactly same distribution. This is an important property of characteristic function, that it is real if and only if distribution of x is symmetric around 0. Just symmetric is not enough, it has to be symmetric around 0. Okay. Now homework is, you can try to derive characteristic function of few common random variables, for example normal or exponential, etc. Let me write down a couple of formulae which you should try to prove. So for example, for let us say discrete, so if I consider binomial NP, then characteristic function is q plus p e raised to I t raised to n. You can see its equivalence to MGF. Okay. Similarly for normal, it is e raised to, so if I have normal mu sigma square, then it is e raised to, so exp, let me write exp I mu t minus t square sigma square by 2. You can see why minus 1, because I square is minus 1. Okay. So try to prove these two. Another important thing is characteristic function uniquely determines the distribution. Okay. So if two random variables have same characteristic functions, then they have exactly same distribution. Okay. So that is an important result. Characteristic functions uniquely determines the distribution. What does it mean? If phi xt is equal to phi by t for every t in R, then distribution of x is exactly same as distribution of y. Okay. Reverse way is of course true. If the distribution is same, then characteristic function would also be same, because while taking expectation we just need distribution. Okay. These are some important properties of characteristic function. We are going to need this when we study central limit theorem. Okay. Many of the central limit theorems are proved in terms of characteristic function because of its existence, which is guaranteed because cos and sine are always between -1 and +1. Okay. So let me stop here. Thank you.